Hello everyone! In this video we will continue to discuss 1.2, topic 1.2, uncertainties and errors, and in particular we will briefly mention linearization. One final note about the document that I sort of start on every time. So I just want to remind you that this is in the Physics 2016 guide, and it always includes some guidance and some data booklet references. So these equations are the ones that appear in the data booklet, and they refer to the propagation of uncertainty that is expected. All right, so in the last video, we discussed how in the future we're going to spend a lot of time sort of propagating uncertainties on graphs by using sort of our best fit line and then a maximum gradient and a minimum gradient, giving us a value for the gradient with an uncertainty on it and a value for the y-intercept and an uncertainty on that. Now, in order to do this, often the fundamental physical relationship is not linear, but we would like to use these graphical techniques anyway. In many cases, what we can do is linearize the data. All right, so let's take an example here. Imagine your independent variable is over here on your horizontal axis, and your dependent variable looks something like this. Now, just so you know, this is transparently the square of the independent variable, but let's say you were taking data and you expected a squared relationship. So you plot it and you get this beautiful parabola. The dependent variable is equal to the independent variable squared. Sometimes it's written as y equals x squared, where y is your dependent variable. You graph your line of best fit, in this case a curve, and sure enough, it's a quadratic or a parabola. Now notice, with this quadratic or parabolic shape, it can be very difficult, and in fact is impossible, to use these linearization techniques briefly mentioned in the last video. Sorry, these uncertainties techniques, that is, the propagation of uncertainties techniques. But if you go ahead and process this dependent variable, then you can come up with a linear graph, okay, using the same data that will allow you to use those techniques, as long as you sort of keep track of what you've done to process that data. So often what we'll do is, instead of sort of graphing just the independent variable versus the dependent variable, we will graph the independent variable versus a function of that dependent variable, or, for that matter, a function of the independent variable. So sometimes we'll be processing the independent variable rather than the dependent variable. In this case, how would we take this data and make it linear? Well, one of the things we could do is simply take a square root of that dependent variable. So if we took f of x is equal to the square root of x of each of these values, then we recover sort of our original values, and when we graph it, it's linear. So as long as we know that this is our original function, so y to the 1/2 power, then we have our independent variable here. So by applying a function with the expected relationship between the independent variable and the dependent variable, we make this linear graph, right? This can sound complicated, a little bit tricky, but it's really not too bad. So let's look at some examples, all right? If your predicted relationship is y equals b, you simply expect y to be constant and independent of x, then you don't need to linearize. Same for if they're directly proportional, or if the relationship is linear. Notice the difference between proportional and linear here. Proportional does not have an added constant. So if you get a constant here, then either you have systematic error or the two values are not proportional. But what if, for example, you had an inversely proportional relationship between your dependent variable and your independent variable? What if you expected the relationship to be such that y is equal to a divided by x, or that y is inversely proportional to x? Well, to linearize this graph, you simply you can linearize it by simply taking y versus 1 over x. So you make a new column here, and in this case you would be processing your independent variable, and you would take 1 divided by your x values, and then you would plot it. And if you plotted y versus 1 over x in that particular case, you would get a linear relationship. This is true for any power law. So any law, any polynomial where you are finding that y is proportional to some function x to the n for any n. In order to linearize this, you would simply plot y versus x to the n. You could also plot y to the 1 over nth power versus x, and that would give you the same result. So y to the 1 over nth power versus x will give you the same result. Notice that a square root is a particular case of a power law with power equal to the 1/2. And so you can see that here. Y to the 1 over n, that is y to the 1 over 1 over 2, is y squared. So y squared versus x is what you would plot to get a linear relationship in this case, or y versus x to the 1/2 power. We are going to see many, many, many examples of this before the program is done, and I will sort of remind you of how this works as we get there. One last word on linearization. So this is a slightly more advanced technique, but I'm including it in this video for completeness. It also shows up on some of the test yourself questions, although I won't be assessing you on these particular techniques until later in the course. So, question, what if we don't know the exact power of the power law? In order to use this linearization technique for any y equals k times x to the n, normally we would graph y to the 1 over n versus x, or y versus x to the n. Both of these would work, but if we don't know n, then we can't do that, right? So we've taken our data and we're not sure what the relationship is. Well, there's actually a technique that will allow you to linearize the data without necessarily knowing n, as long as the relationship is a power law. And that's by using a logarithm. So here's how it works. Y equals k x to the n can be processed by taking a logarithm of both sides. So we take the log of y, and we take the log of k times x to the nth power. Notice that this is equal to log of y equals n times log x, plus log k. My bad, that is an error in here, and that will be an error in here. That's all right. So that's fixed. So that function is log of y is equal to n times log of x plus log of k. And you can see that all I did is take a logarithm of both sides. So this captures the same relationship. Now notice that if I graph this, that is, if I graph log of y as my variable and log of x as my independent variable, then I should get a linear relationship here, no matter what this n is. And the slope of that linear relationship between log y and log x will be exactly equal to the exponent in the power law. So if it turned out that exponent was a 4 rather than a 5, which perhaps we didn't know, that would tell us something about the relationship between y and x. And although we had to assume that it was in the form of a power law, it turns out that we could discover what that power was. Notice that the y-intercept of this particular graph will be equal to log of k. And you can verify that with log properties if you wish. So this is how we measure an unknown n for a presumed power law, and is a general way of linearizing any power law. So you can do this. Often it's straightforward if you know the relationship, but when in doubt, you can always take the logarithm of both your y and your x, and if it is a power law, you will be able to measure from the slope what that exponent power, what the power is.